is also known as Newton's law of cooling. And basically this is a definition of heat transfer coefficient. It is not actually a law, but it defines the heat transfer coefficient. And as I mentioned, since near the surface the heat transfer rate is by conduction, we can show that Hc is nothing but minus Kf dt by dy at y is equal to 0 divided by Tw minus T infinity. By writing the heat transfer rate in terms of conduction for the stationary layer and equating that to Newton's law of cooling, you can arrive at this expression. Now the convective heat transfer coefficient from this equation obviously depends upon the thermal conductivity of the fluid, the temperature difference Tw minus T infinity, and the temperature gradient dt by dy at y is equal to 0. That means what is the temperature gradient near the surface. Now this temperature gradient near the surface dt by dy at y is equal to 0, y is the direction perpendicular to the surface, so keep it in mind. So dt by dy at y is equal to 0 depends on the rate at which the fluid near the wall can transport energy into the mainstream. So it basically depends upon the fluid flow. That means in convective heat transfer problems we have to consider fluid flow in addition to the heat transfer. That means this mode of heat transfer is governed not only by the heat transfer laws, but also by the fluid flow laws. So some people do not consider convection heat transfer as a basic mode, because here you have both heat transfer by conduction as well as fluid flow. Okay, but still for convenience sake we consider this also as one of the basic modes of heat transfer. Let me show typical convective heat transfer coefficients. This table shows the type of fluid and flow. Remember that once again I am repeating it, convective heat transfer coefficient depends on the type of the fluid and on the flow and also on the geometry. And if you have air in free convection, that means heat transfer is driven by density differences, then heat transfer coefficient varies between 6 to 30 watt per meter square Kelvin. And if you have water again in free convection, then you have heat transfer coefficient slightly higher, 20 to 100. So you can see that water is gives a much higher heat transfer coefficients compared to air. This is due to the higher thermal conductivity of liquid. Then if you have forced convection, then you have higher heat transfer coefficients. Forced convection and the fluid is air or superheated steam, then the heat transfer coefficient varies from 30 to 300. So you have one order of magnitude higher than the free convection. This is because of the vigorous mixing of the fluid when you have forced convection. When you have oil in forced convection, again you have 60 to 1800. This is higher than the air because you are dealing with a liquid. And if you have a water, you get much higher heat transfer coefficient because water has typically a higher thermal conductivity compared to oils. And if you have phase changes such as boiling or condensation, you get really high heat transfer coefficient. For example, in case of synthetic refrigerants, under boiling condition you have heat transfer coefficient which vary anywhere between 500 to 3000 watt per meter square Kelvin. And if you have water, then you get really good heat transfer coefficients, again because water has excellent thermophysical properties compared to synthetic refrigerants. So you can get heat transfer coefficient from 3000 to 60,000. And similarly in condensation, generally condensation gives much higher heat transfer coefficients compared to any other mode of heat transfer. So you can see that you get very good heat transfer coefficients when fluids are condensing. Typically with steam you can get heat transfer coefficient as high as 1 lakh watt per meter square Kelvin. Now similar to conductive and convective heat transfer, conductive and radiative heat transfers, you can also write the convective heat transfer rate in terms of the temperature potential and the resistance. So you can write Q as Tw minus T infinity divided by R convection, where R convection is the heat transfer resistance to convection. And if you compare this equation, you can easily show that R convection is nothing but 1 by Hc into A. And the major problem in all convective heat transfer problems, the way it has developed, is the estimation of heat transfer coefficient. So you can see that almost the entire literature on convective heat transfer coefficient is devoted to evaluation of heat transfer coefficient, because once you know the heat transfer coefficient, you can find out the heat transfer rate by multiplying that into temperature difference and surface area. Now how do we evaluate the convective heat transfer coefficient? You can evaluate it analytically for simple cases. If you want to evaluate it analytically, you have to solve mass, momentum and energy equations. Since this can be pretty complicated, this method is possible only for simple situation. Simple situation means, let us say that laminar fluid flow is taking place over a flat plate. Then you can have analytical solutions and you can find analytical expressions for heat transfer coefficient. Similarly, laminar fluid flow is taking place over a cylinder. Again, you can have a closed form solution and an analytical solution. But when you have complicated cases, for example, when you have turbulent flow and when you have complicated geometries, then it is very difficult and you cannot have analytical solutions. And in such cases, what is done is you have to go either for numerical methods, or most popularly people use experimental methods in addition to the dimensional analysis to arrive at expressions for heat transfer coefficients. That is what is mentioned here. Most of the convection heat transfer data is obtained through careful experiments, and equations suggested are mostly empirical. Once you have empirical equations, they are valid for only a set of conditions under which these equations were derived, and they are also applicable to only that particular range of experiments. So you must be very careful when you are using the empirical correlations. You must check that your problem falls in the range of that particular correlation, only then use it. And fortunately, because of the huge amount of work done in this area, you have correlations for almost all practical situations. So you have to look for them in suitable heat transfer data books and textbooks. And to some extent, generalization has been made possible by introducing several non-dimensional numbers. Usually you will see that, probably you remember from your basic course on heat transfer, that several non-dimensional numbers such as Reynolds number, Nusselt number, Prandtl number are introduced, and generally the correlations are given in terms of the non-dimensional numbers. This will generalize the correlations to a large extent. I will show you one typical heat transfer correlations. This is known as Dittus-Boelter equation, and this is valid for fully developed turbulent flow inside smooth tubes. So this is valid for smooth tubes, and it relates a non-dimensional parameter Nusselt number, which is defined as the Hc d by Kf equal to 0.023 Re to the power of 0.8 and Pr to the power of 0.n. So Nu is the Nusselt number, and it is equal to Hc d by Kf, where Hc is the convective heat transfer coefficient, d is a length parameter, and Kf is the thermal conductivity of the fluid. And on the right hand side you have Reynolds number Re, and also you have another dimensionless number known as Prandtl number. Prandtl number is defined as, you can see here, Prandtl number Pr is Cp mu f by Kf. All the properties are that of the fluid, that is why the subscript f stands for fluid. So Prandtl number is Cp mu by K, which can also be written in terms of kinematic viscosity nu divided by the thermal diffusivity alpha. So Prandtl number is basically nu by alpha, and this Dittus-Boelter equation, there is another parameter n, and this n will take the value of 0.4 for heating. That means when the fluid is getting heated, you have to use a value of 0.4 for n, and if the fluid is getting cool, then you must use a value of 0.3. This is a very popular empirical correlation, very widely used for, as I said, for fully developed turbulent flows inside the tubes. And if you are using a hydraulic diameter, you can also use this to non-circular tubes. But this is again valid for certain Reynolds number range, and this is also valid for certain Prandtl number range. So when you are using this equation, you must know what is the range under which this can be used. This is just one example of a typical convective heat transfer correlations. A large number of correlations, as I mentioned already, are available for a wide variety of flow situations. That means you have heat transfer correlations for force convection, free convection over flat plates inside the tubes, and heat transfer correlations for phase change, boiling, condensation, etc. So all these things have been derived and they are available. So we will be discussing these things in detail when we are designing evaporators and condensers in later lectures. Now let us quickly look at mass transfer. Mass transfer takes place when a system containing two or more components whose concentration vary from point to point, then there will be a natural tendency for mass to be transferred so that the concentration difference can be minimized. That means when you have a system which consists of 2 or more constituents or components, and if there is a concentration difference, then the spontaneous process is to reduce the concentration gradient. That means there will be mixing of the components. That means there will be mass transfer. That means transfer of one constituent into other. This is what is known as mass transfer. So, the mass transfer can be defined as the transport of one constituent from a region of higher concentration to that of a lower concentration is called as mass transfer. Why do we study mass transfer in refrigeration and air conditioning? Because we in refrigeration and air conditioning we typically encounter several cases where mass transfer takes place. A typical example of mass transfer which all of us are familiar with is that of drying. For example, when you leave a wet cloth in an unsaturated or dry air, then the cloth becomes dry. So, what has happened? Water vapor or water from the wet cloth is transferred from the cloth to the surrounding air. So, this is one popular case of mass transfer. So, we have this typical drying problem in air conditioning, because air conditioning latent heat is involved. So, we will be applying these principles when we are solving those problems. Another very familiar case of mass transfer is the spread of perfume. For example, when you put a perfume in one corner, because of the diffusion the perfume spreads all over the room. So, this is another example of mass transfer. Now, let us look at some very basic equations of mass transfer. The first basic equation is what is known as Fick's law of diffusion. This law deals with transfer of mass within a medium by molecular diffusion process, and it is given by m dot A is equal to minus dAb A dCA by dx, where dAb is known as a diffusion coefficient for component A through component B, and dCA by dx is the concentration gradient. So, you can see the similarity between Fick's law and Fourier's law for heat conduction. The similarity arises because both are diffusive processes. So, that is why the equations are similar. Again, you can see that just like Fourier's law of heat conduction, you also have a negative sign here. This means that mass transfer always takes place from a region of higher concentration to a region of lower concentration. And similar to convective heat transfer, we can also have convective mass transfer. This takes place whenever a moving fluid between a moving fluid and a surface, or between two relatively immiscible moving fluids. For example, you have, let us say, the two fluids, two different fluids which come in contact with each other. Okay, then for example, you have a concentrated sugar solution and you slowly pour water over that. So, you have two different fluid layers, and slowly sugar spreads throughout the solution, and the entire solution reaches a uniform concentration. So, mass transfer takes place in this process. So, this is a typical example of convective mass transfer. And similar to Newton's law of cooling for convection, we can also write convective heat mass transfer as m dot is equal to Hm A into delta Ca, where Hm is the mass transfer coefficient, A is the mass transfer area, and delta Ca is the concentration difference. Now, let us look at the analogy between heat and momentum transfer. This is very interesting. We have seen that the mass transfer, momentum transfer, and heat transfer by convection all appear to be similar, because all of them have many peculiarities. For example, between momentum and heat transfer, you have a hydrodynamic boundary layer which takes care of the momentum transfer, and analogous to that you have a thermal boundary layer. Because of no slip condition, velocity becomes 0 on the surface, and similarly the fluid temperature becomes that of the surface temperature, again because of the no slip conditions. And mathematically, if you look at, for example, you take a case of laminar fluid flow over a flat plate. If you look at the momentum equation and the energy equation, you will find that they are exactly identical when Prandtl number is 1, and when there are no pressure gradients in the direction of flow, and when there is no viscous dissipation, and when there are no heat sources, then you will find that momentum and heat transfer equations are exactly identical, and if they have similar boundary condition, the solutions also will be identical. So, that means there is a direct analogy between momentum and heat transfer. This is the observation, and for this condition it can be easily shown that a non-dimensional parameter Stanton number, which is given by Nu by Re into Pr, which is equal to Hc by rho V Cp, where V is the fluid velocity, is equal to F by 2. So, this is known as Reynolds analogy. So, what is the use of this Reynolds analogy? You can see that Reynolds analogy connects heat transfer coefficient Hc with friction factor F. That means, if we know the friction factor, you can find out the heat transfer coefficient by applying this analogy. You do not have to carry out any heat transfer experiments. So, this is very useful. This Reynolds analogy is strictly applicable for Prandtl number 1. So, Colburn has improved this for different Prandtl numbers, and he has arrived at this what is known as Colburn analogy. This is given by Stanton number into Prandtl number to the power of 2 by 3 is equal to F by 2. This is known as Colburn analogy. This is applicable to a Prandtl number varying from about 0.6 to 50. So, this is you can see the usefulness of this. Now, let us look at analogy between mass and momentum transfer. Similar to heat and momentum transfer, we can also write analogy between momentum and mass transfer, and here we define another non-dimensional number called Sherwood number SH, and this Sherwood number is defined as Hm into L by D, where Hm is the mass transfer coefficient and D is the diffusion coefficient and L is a length parameter. So, Sherwood number is analogous to Nusselt number, and we also define another non-dimensional number called Smith number. This Smith number is analogous to Prandtl number. So, when you are applying this analogy, you can show that mass transfer coefficient Hm divided by the velocity is equal to friction factor divided by 2. This is valid for Smith number equal to 1. So, to take care of the Smith number other than 1, we can modify this similar to Colburn analogy, and we have the modified analogy given by Sherwood number divided by Reynolds number into Smith number to the power of 2 by 3 is equal to F by 2. This is the analogy between mass and momentum transfer. Now, if you compare analogy between mass and heat, momentum and heat transfer, and momentum and mass transfer, you can arrive at this important expression. You can look at this. You can show that the heat transfer coefficient divided by the density into specific heat at constant pressure and Hm is equal to alpha by D to the power of 2 by 3. Okay, so this is from the comparison of the two analogies. This is a very useful expression, particularly for air conditioning calculations, because for air conditioning calculations this parameter alpha by D to the power of 2 by 3 called as Lewis number LE, this takes a value of 1 for air water mixers, not exactly 1, but it is close to 1. So, when this is close to 1, then your heat transfer coefficient is nothing but a product of density into specific heat into mass transfer coefficient. So, if you know the heat transfer coefficient, directly you can find the mass transfer coefficient. So, this is very useful, and we will be applying this when we do the air conditioning calculations. Now, let us look at multi-mode heat transfer. So far we have been discussing and we have been describing the different modes of heat transfer separately. First we have given equations for conduction heat transfer, then convection heat transfer, then radiation heat transfer. That means we have delinked the different modes. But as I have mentioned, in most of the engineering problems, the heat transfer takes place by more than one mode at the same time. That means you have what is known as a multi-mode heat transfer. So, let us see how we look at how we solve the multi-mode heat transfer problems. As I said, in most of the practical heat transfer problems, heat transfer occurs due to more than one mechanism, and using the concept of thermal resistance which we have developed earlier, it is possible to analyze steady state multi-mode heat transfer problems in a simple manner similar to electrical networks. So, remember that this concept of thermal resistance and networks is applicable only to steady state problems. If you have unsteady state problems, you cannot directly apply the concept of thermal resistance and networks. Okay. Now, let me give an example of a building wall. Okay.